This is Computer Programming 1 from the University of Washington. I'm Martin Dickey, and I'm very happy to have another chance to talk about one of my favorite topics, recursion. Today, we'll not introduce any new concepts of recursion or of the C language. Instead, we'll take a familiar problem and we'll solve it again using recursion. The problem we'll solve is searching an array, and the algorithm we'll apply is the binary search algorithm. We studied this sometime earlier in the course. You remember there's an essential precondition for binary search to work. The array that's being searched has to be sorted already. Now, if this condition is met, then here's what you can do. You look for the target in the middle of the array. If you don't find it there, you at least know which half of the array to continue looking in. Remember how we took the phone book and were able to throw away half of it each time we looked up one page. Let's take this algorithm and apply it again to develop a recursive algorithm. The original algorithm is based on the following observation. At any given point in time, we can think of the array as having three parts. There's a part where we know the values are all less than or equal to x. There's a part on the right where we know the values are all greater than x. And then in the middle, there's an unknown part. It's marked in green with a question mark. We don't know how those values relate to x. If we go to the middle and look at the element there and compare it with x, we're then able to move L up into the green region or R to the left into the green region. The result of this is that our green region has shrunk by half, and we're making rapid progress toward eliminating the green region altogether. Once we eliminate the green region, we're done, because the value, if it exists, must be at position L. The key idea is to do a little bit of work in a function and then make a recursive call to do the rest. We won't need iteration at all. The binary search has a value that's restricted to the range. All we'll need to do is look at the midpoint in order to decide how to proceed. Once we know which direction we have to look in, we can make a call to binary search which correctly will examine the remaining part of the unknown area of the array. As we learned when we first talked about recursion, there are two essential elements in every recursive function. One of these is a base case, and some problems will have more than one base case. This is something that can be solved or determined immediately without having to use recursion. The base case for binary search is that there's no longer a green area. We know the status of all of the values. In this case, we can conclude by looking at a single value, the one at L. The way we'll recognize this in the program is with the simple test, is L next to R, i.e. is L plus 1 equal to R. So the base case is one of the things we have to have. The other thing we'll need in any recursive function is one or more recursive cases. These must be cases that get us closer to a base case and do so by making a recursive call to the same function. What is the general case from which we want to make progress? Well, in general, it will be like this. There will be a green region of some size. To make progress with this, we want to move L over to the right or R over to the left to shrink the green region. Each recursive call will be given a different set of L and R values. Now, this introduces a slight difference between the function that we originally called to solve the problem and the one we're going to be writing now. The original search problem passed an array, the size, and the target value to the function. In order to use recursion, I will need to know both the values of L and R. So my function has to have 4 parameters: the array, L and R, and the unknown value. To emphasize the fact that this is a different function from the original binary search, let's give it a different name. Let's call it the binary search helper. We're now able to code the binary search helper directly by applying the analysis we just made of the base and recursive cases. The base case is detected by seeing if L plus 1 is R. If so, the value we want to return is L. Let's come back to that in a minute. In the recursive case, we want to make progress by determining which of L or R to adjust. Then, having done that, having changed one of those two, L or R, we'll make a recursive call to binary search helper. It passes it A, L, R, and X. Now this may look exactly like the original call, but it's not. The values of either L or R are going to be different, and they will define a smaller range. So we are, in fact, making progress to our base case. Let's pause and note the value that's being returned in the base case. The overall binary search function is supposed to return a -1 if the answer is not found, and it's supposed to return the index if it is found. Binary search helper, though, doesn't make this decision. It's simply returning L as a way of saying where the split point is in the array once all the status of everything is known. It looks like we're going to need some additional code somewhere to make the final decision about whether to return a -1 or something that's an array index. We have another piece of code that has to be done somewhere as well. The first time we call binary search helper, we want to tell it that the entire array is unknown. This means initializing L to -1 just to the left of the array and R to N just to the right of the array. Now we can't do this initialization inside binary search helper because L and R are parameters. They already have values at the time the function is called. They're going to have to be code outside binary search helper that makes this initial call correctly once only. Okay. Likewise, there needs to be code that makes the final return result. That also cannot be placed inside binary search helper. The reason is that most of the time when binary search helper returns, it's just returning to another copy of binary search helper, not to the original caller. We can solve both of these dilemmas by defining an additional function, sometimes called a wrapper function. It does two important things. First, it sets a recursion in motion. It calls the recursive function, binary search helper, with the correct initial set of parameters. Then after that function returns from all of its recursions, the wrapper function can determine the correct final answer. Here's the code for it. It's interesting to note that it is not recursive. It goes straight through its code, makes an initial call to bsearch helper, and then based upon the result, the L value sent back from that decides what value to return to the original caller, either L itself or a -1 indicating that the value was not found in the array. This is a common technique when dealing with recursive functions. It often seems necessary to take the original function as a non-recursive element of the design and from that call the part where the recursion will actually take place. Let's trace this, not in great detail because I think you see the principles now, but let's just do one example to convince ourselves that in this one case it's going to work. Let's call bsearch, giving it the array of size 8, and look for the target value of 5. Okay, you might think ahead and ask yourself, what should be returned from this function? Well, 5 is not in the array, so eventually we should return a -1. bsearch makes one call to bsearch helper and passes it L and R values that bracket the whole array. So the L index is -1, the R index is 8. Picture the R index is pointing just past the right end of the array. Now, the first time bsearch is called, it will look in the middle of the array. Where is that midpoint? Well, it's -1 plus 8, which is 7, divided by 2, which is 3. So it will be looking in position 3 of the array. It will not find the 5 there, but it's able to determine that the answer, if it exists in the array, must be on the left-hand side. So it will change the R value for the next recursion call. And that's what happens. In the second call to bsearch helper, L is still -1, but the R value has been moved down from 8 to 3. 3 was the midpoint in the first call to bsearch helper. Okay, well, you can trace down what happens. The next time we're going to move L up and call for a search between 1 and 3. The next time we're going to move L up again and call for a search between 2 and 3. This search is our base case. L is adjacent to R. When bsearch helper recognizes this, it will execute a non-recursive operation and send back the value of L, which is 2. That value is sent back to bsearch that called it, and each bsearch does nothing with that value except to return it to its caller. Eventually, that value comes back to bsearch itself. It's coming back from bsearch helper in all these cases, by the way, not from bsearch. Bsearch gets the 2 back, and it looks at position 2, asking the question, does position 2 of the array contain the target value 5? The answer is it does not. It contains a 3. And so bsearch will return a -1 to its caller. And that's the answer we want binary search to return. You might want to take some other values and try them out. You might try this trace with a value that is in the array, like a -17 or a 12. You might try something that's not in the array on the upper end, like a 143, or on the lower end, like a -143. These are values we traced with the iterative version when we saw that. Binary search can be programmed either way. It turns out that any algorithm can be reworked to use recursion. And it's also true that any recursive algorithm can be reworked to use iteration. However, that reworking is not always straightforward. It's not as simple, for example, as rewriting a while loop as an if loop. The two programs, the iterative and the recursion versions, could look vastly different. So in some sense, this is kind of a theoretical result. In principle, given care, we could find an iterative version from a non-iterative version and so forth. But the program we come up with might not be a very interesting or a very understandable one. There are actually some programming languages where recursion is the only choice. Pure Lisp is like that. Prolog is like this. So programmers who use this language come to find it a very natural way of doing things. On the other hand, programmers who first learn iteration sometimes find recursion a difficult concept. There are some algorithms that just seem more naturally written with recursion. When we talked about recursion the first time, we saw that 3n times 1 function. That was originally given to us as a recursive algorithm, and there wasn't any obvious way to do it non-recursively. Sometimes, however, if you use recursion, the result can be an inefficient algorithm. That will also be a consideration. However, deciding what's efficient and what's not efficient is not a simple matter of staring at the program or counting lines of code. It takes more analysis than we'll do in this course. There's another case in which recursion is often superior. In advanced programming, the data structures we use often have a recursive flavor of their own. And if this is the case, a recursive algorithm will often be more natural, shorter, more elegant, more simple to understand than a non-iterative version. How do you know when you should use recursion? If the problem has a couple of simple cases plus a couple of cases which seem to be copies in some sense of the original, then you might think about using recursion as a natural way to express the problem. I might add, as a teacher, there's another case when you should use recursion, and that is when you're learning the concept and you just need practice on it. Sometimes doing problems recursively is helpful as a skill sharpening tool, even though for real programming you wouldn't want to solve the problem that way. Let's wrap up. We've seen that programming with recursion is an interesting new technique. It allows us to do repetition without using iteration. The way it works is nothing new. It's just a consequence of the way that function calls and local variables work. But beyond the programming aspects, recursion is more than a programming technique. It's also an approach to solving problems and even perhaps a way of thinking about the world. Please join me as this course continues.